Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine developer. In this tutorial, I'm gonna show you how to do precipitation downscaling from 10 km to 1 km resolution using Python API programming and Earth Engine assets. So, if you want to learn how to do this procedure using deep learning approach, let's follow this tutorial. Okay, make a new notebook in the Colab environment first. We need to install essential libraries to deal with the Earth engine in the Python API programming. So let's start with the most important library, that is Xarray library. I need to install an upgraded version of Xarray like this. If you have no information about the Xarray, open your browser and search about Earth Engine and Xarray library. As you can see, there is a GitHub page. There you can find a detailed instruction about Xarray library characteristic. In this library, we can incorporate Earth Engine and Xarray data formats that allow us to apply a Python algorithm on the Earth Engine datasets. It is awesome. So let's clear the output after installation. So in the next step, I need to do the same process, this time for GEE map. The GEE map is another useful library developed to deal with Earth Engine resources in the Python API programming. The GEE map offering additional resources to work with the Earth Engine platform that make Python API programming much easier for the Earth Engine users. So let's clear the output. Two essential libraries already installed, and now we need to import the main library, the Earth Engine library. As it is built-in available in the Earth Engine in the Python or Colab environment, we don't need to import it again. We don't need to install it like Xarray and GEE map. Okay, now I need to establish a connection between Earth Engine and Colab environment. Let's start with authentication and let's initialize Earth Engine account. Every user has a personal account in the Earth Engine. So we need the account project ID. If you want to know how to find it, just open a browser or open a tab in your browser and go to Earth Engine code editor environment, just like this. In the code editor environment, upper right, you can find your account information. Go to the account information and then project info. For example, my cloud project ID is this, and you can find yours from the same way. So let's import, and the next item here is the OPT URL. If you the OPT URL refers to the server address, the Earth Engine server address. You can find it in the GitHub page, in the Xarray page. If you scroll down a bit, here OPT URL or Earth Engine server address is available. Paste it, just like this. Let's run the code, and Colab asking you permission to access to the associated Earth Engine account. So just select your account, click on continue, and continue, just like this. It's working properly. If you faced with any challenge in this tutorial, you can go to my YouTube channel, find this video. Below this video there is a code example there, and you can compare my code with yours, and then easily you can fix the issues. So now we need to find the region of interest in the first step. Remember that this tutorial is extendable to all around the world. You don't need to limit yourself to the area that I'm working on. You can use your own study area as well. So to select the study area, the GEE map giving us a user interface to do it simply. So let's import the GEE map, and from GEE map I'm making a map variable. There from GEE map a function like map created. So and let's print the map. After a few moments, you have a user interface, including a global layer and drawing tools available here. You can easily find your region of interest without any challenge. So, for example, I'm as an Iranian prefer to select a part of my own country. So, as you can see here, I prefer to select a part of northern area in my country. For example, here, uh, this area highly actually receiving precipitation during a year compared to the rest of the country. So I prefer to select an area in this, to select the region of interest from this area. So scroll down a bit, and now we need to have the selected area as a variable. Make a new layer, make a new variable ROI, and from the map we want to select the last feature that you draw. So convert it into a geometry just like this. Let's print the ROI at the end. So as you can see, the selected area now available as a polygon with associated coordinates, meaning that we can narrow down a study or our analysis to the selected area that is ROI in the code. So the study area selected. Now we need to find the precipitation data for the downscaling process. Hopefully, several precipitation datasets available in the Earth engine. For example, one of the most famous one is the Global Precipitation Measurement System (GPM) datasets. Let's open a new tab in your browser and search about Google Earth Engine, GPM monthly precipitation dataset, just like this. Now you can find the GPM monthly precipitation dataset. As you can see, it's available since 1998 and with around 11 kilometer resolution. That precipitation data is available millimeter per hour. So the Earth Engine snippet is available here, and we can call this dataset into the programming code. Make a new variable like PR, make a tuple, and paste the collection snippet. Define a filter date. Filter date starting from time start to time end. Let's make a variable like time start with a date format. For example, I prefer the time span starting from 2002 to 2025. So time end ee.date 2025. I prefer to select the long-term period for the analysis because in the downscaling process, I need to have a huge data set that shows the dynamic fluctuation or variations of precipitation through different years and different months. And that helps the model to make a better prediction for the higher resolution data set. Okay, now precipitation data calling for these over 23 years, for this, for example, 23 or 22 years. There are different bands available here, but I prefer to select the precipitation layer that is the target one. So let's select the precipitation layer. The precipitation selected. If you want to use a simpler and shorter name format, you can make another bracket like this and enter the new name that is simpler and shorter. The simple and short name easier to call in the next step because Here, in this process, we are dealing with a large number of variables, and it is better to have a simple name to deal with. So let's call the PR and see if it is works. And as you can see, over 270 elements available during this period of time. In every dataset, the precipitation with date acquisition format, all of them are available. Okay, we have a dataset with 11-kilometer resolution. It's available for all around the world, unlike the other precipitation dataset in the Earth engine or in the remote sensing that only covers areas for areas up to, for example, near Nordic area or near, for example, high latitude areas, and not completely cover the whole of the world. But the GPM covering whole of the world and without any challenge. You can call and use this data set for all around the world, and you will have no limitation even for high latitude areas. So now I need to call some predictors for the downscaling. Okay, the precipitation itself has coarse spatial resolution. I need some predictors that naturally correlated with the precipitation. Something's explaining the, for example, the vegetation, the temperature, evapotranspiration, and land cover, topography. All of these parameters directly or indirectly associated with the precipitation, and hopefully they have higher spatial resolution around 1 kilometer using MODIS dataset. So we can use that datasets as a predictors because they are correlated with the precipitation and same time offering higher spatial resolution. That's why I need to call the predictors from MODIS datasets now. Okay. The first predictor, for example, could be about the vegetation that is related to the precipitation. So, for example, if we have the higher precipitation, then definitely we will have higher amount of the green areas in the study area. So, open a new tab and search about Google Earth Engine MODIS NDVI or MODIS vegetation product with 16 days frequency. Remember that here precipitation available in the monthly format, and all the predictors must have the monthly format as well. In the next step, I'll show you how to convert them into a monthly format at the end. So the terra vegetation indices 16 days available, and here you can call this data set. You can see its spatial resolution is around 250 meter, but finally I will resample all of the data sets into the 1 kilometer. The MODIS dataset ranging from 250 to 1 kilometer depends on the kind of the product and variable. It varies, but I show you how to resample them all into a single spatial resolution at the end. But it's important all of them have higher spatial resolution compared to the precipitation, because that's essential concepts in the downscaling process. So as you can see, the Earth Engine snippet available, and let's copy and paste. Define a filter date based on time start and time end. It is important all the predictors available in the same period of time that original variable is available. Let's select the target variables. So here there are two proxies for vegetation cover. One of them is NDVI and the other one is EVI. Let's select the both NDVI and EVI in the first bracket. EVI the first bracket. I need to convert them into a small letter format. Let's make another bracket and enter the new names like NDVI and EVI with a smaller format. So now here we have vegetation layer. Let's call, and code is running. As you can see, over 500 elements available in all the dates You can see two bands available, NDVI and EVI. In the properties, the system time start is available as well. As we are working in the time series analysis, it's important to have the data acquisition for all of the data sets, because we need something to actually match the data into a single image collection, and that's the key parameter is the system time start, and based on we can find the associated data for each month separately. So the vegetation dataset is available, although there is a scale factor here, but in the deep learning approach to predict something newer, in this application specifically, it's not essential to add or apply the scale value, so or the scale factor, because it doesn't have a significant impact on the quality of our estimations. That's why I'm not applying the scale factor on the vegetation or the rest of the data sets. So now another data set could be, for example, the temperature layer. You can go to net and find Google Earth Engine MODIS temperature dataset with 8 days frequency. So the multi-temporal dataset like 8 days, 16 days, or monthly format is much better than the daily format, because they are offering a higher quality dataset with the lower noises, including the cloud impact. And that's why we can have a much better estimation at the end. So as you can see, the Terra land surface product is available with 1 kilometer resolution. That is good still, because the target resolution is 1 kilometer for the downscaling process. And you can call this dataset as well using Earth Engine snippet. Make another variable like temperature here and paste the collection, the temperature snippet, call it for the same period of time using time start and time end. Time start and time end. So let's select the target variables. The target variables including LSD day and night. Open the first bracket, enter LSD day 1 kilometer format and LSD night. LSD night 1 kilometer format. So now I need to add the new names like temperature day and temperature night. Let's print the temperature as well. Here you can see over 1000 dataset is available here for the period of time, but we will convert all of them into a monthly format at the end. So this is about the temperature data. The next data set could be, for example, evapotranspiration. Open a new browser and search for MODIS evapotranspiration gap fillet format. Evapotranspiration gap fill version. So TerraNet evapotranspiration gap fill version is available with 8 days frequency. Let's call it using Earth Engine snippet. ET, paste the collection snippet, filter it based on time start and time end. Select the target variable, that here is ET. These products offering 500 meter resolution. Target band is the ET. The new name is the ET, small letter format. So, and the ET is called. Let's make a print to ensure that everything's fine. And there is no problem. Yes, over 1000 elements is available. For each date, we have ET with system time start. So, okay, now let's convert these variables into, for example, the monthly format. How we can do this? I need to make a new function to get each image collection and filter it based on each month and calculate the average or aggregate it into monthly formats. So now we have a start date and end date. First of all, we need a list of monthly dates. So let's calculate the differences between time end and time start based on number of the months, and then make a list. The list starting from 0 to the number calculated by the time differences. Remember to round it to avoid any potential problem, and subtract by 1 the list starting from 0 to this number. So as we are starting the 0, it's necessary to subtract it by 1. So make a loop structure and define a function. Each number in the list will be replaced by the date calculating through this equation. Time start going advance or going forward by x month. X is the number already calculated by time difference. So let's print the time list and see how it is working. Now we have a list of dates starting from January 2002 to the December 2024. Okay, the time list now is available. I can filter all collections based on this date list and calculate the associated average for each month separately. So another function is necessary here. Define a function beginning with def. The function name here is the monthly. The function is hosting two arguments. The first is the date list, the next is the collection. So we need to extract the start date from the date list that you can see it's available in the date list. So now we need an end date for each month. The end date sets to start date already available. If you go advance by 1 month, the end date will be calculated. We already have the collection as well. Collection, aggregated collection, sets to get the collection, filter it based on each month, start date and end date. Let's calculate the average by min. So return the aggregated collection with a new system time start. Now we need a system time start explaining the date acquisition for the data sets. So call the start date, convert it into the millisecond format. Okay, the monthly format created, the monthly function is created. As it is a row function, now we need to apply on predictors like vegetation, temperature, and evapotranspiration. Okay, now I need to calculate the monthly vegetation as well. Make a new variable, define an image collection format, call the time list, and apply this function. The function gets each date from the date list and also applies on vegetation data sets. Now the monthly data set is available. As you can see, 276 elements again is available. Here the 16 days, the NDVI now converted into the monthly format. That's why we have the monthly NDVI with lower number of elements. So you can see two bands available with the system time start information. We need to repeat this process for all of the image collections. Now let's try for the temperature datasets. Temperature monthly format, Earth Engine image collection, call the time list, define a loop, and apply the function lambda, call the lambda, get the time list, x temperature, temp monthly. Now again, same number of images returned because they have monthly format. This time, temperature for day and night is available. Now let's repeat for evapotranspiration, ET monthly format, Earth Engine image collection, get the time list, apply lambda x monthly xet, et monthly. Again, same number returned, only ET available with the new system time start. So to ensure that system time start format is same as the other predictors, we need to apply the monthly function on precipitation as well. Although precipitation data set available with monthly format, but I need to make sure the system time star format is same between the predictors and precipitation, that is original variable. So let's repeat this process for monthly vegetation. Image collection, call the time list, call the lambda, the monthly format on date list and precipitation. PR with monthly format. Nothing changed in the precipitation, just we make sure everything is same about the system time start between predictors and original variables. So now I need to make a single collection including the original variable and all of the predictors. So define or make a new variable that is a collection. Get the monthly vegetation first. Monthly vegetation. Let's combine with the monthly temperature and combine with monthly evapotranspiration and combine with monthly precipitation at the end. Let's print the collection. Now we have 276 elements again, but this time for each date we have 6 elements, including the predictors, multi-temporal predictors, and original variable. But it is good to have the land cover and topography as extra or additional predictors in our study, because the precipitation is also correlated with the topography and also the land cover. So let's make a new variable for the land cover. Open a new tab in the browser and search about Google Earth Engine MODIS land cover datasets. Here you can find the monthly land cover dataset with 500 meter resolution. So select the land cover snippet, make a tuple, filter it based on time start and time end. So I prefer to have one single land cover that's showing the most frequent classes that is that you can calculate using mode function. So let's select the target band that is LC type 1 here. Okay, and yes, that's fine. Let's convert the name into a simpler one like LC. Yes. Okay, the land cover is ready. And also we need the topography dataset as well. Open a new tab in the browser and search about Google Earth Engine GTopo. GTopo. It's a digital elevation model with 1 kilometer resolution. And you can call this topographical layer using image snippets, just like this. Only one variable. We can rename it to, for example, DEM. Okay, now there is a problem. How we can add these two data sets into a collection, because they are not they are not known as a multi-temporal data set. They are single data sets, but we need to have them for each month separately. It's very easy to do. Just call a new map like this and define a lambda. Each input into the function considered as x. For each data set in this list, I want to add a new band that is land cover and the topography layer. Let's run. And now you can see the land cover and topography both are available as an additional band or predictor for each month separately. Here you can find them easily here. Okay, the dataset is now prepared for the deep learning process, and now it's the time to convert this image collection into an Xarray format. This is the main step that we want to use the XEE capabilities. Okay, the XEE works with Xarray format. Let's call the Xarray as XR and make a new variable, a dataset with 10 kilometer. Now I need to call this dataset with 10 kilometer, but in the next step I'll show you how to call with 1 kilometer and how to do the downscaling as well. So 10 kilometer datasets. From XR, call the datasets. The input data is a collection and the engine protocol EE. The CRS, the coordinate system of this dataset, is 4326. This is a unique ID for WGS84 that is unique for all around the world. And the scale value, as I need to call this dataset with original resolution, that is the 10 kilometer or 11 kilometer, so it's essential to have the scale like 11 kilometer or 10 kilometer. So the scale is based on a degree, 1 degree 100 kilometer roughly, and 0.1 is the 10 kilometer. The region of interest or geometry is the ROI. So something's wrong here. There is no data set in the XR. That's my fault. I should use open data set, just like this. Let's run the variable, and now I'm waiting to see the result. Okay, the data set now converted from image collection into a multi-dimensional structure or Xarray format. You can see these are the same data set, but image collection format no longer available. Now the dataset converted into a Python-friendly format. That's why we use the XEE library. The XEE now help us to use the Python resources for the satellite data processing. That's very interesting things. We can use the unlimited resources in the Python for the Earth Engine datasets. And now we can do a lot of things that we couldn't do before in the Earth Engine code editor environment. That's perfect things. So instead of the bands, here we have the variables and also the each dimension, temporal and spatial dimension, both of them available in different, as you can see, dimensions and array, and we can easily do the analysis on these huge data sets. Okay, now I'm gonna show you how to deal with this data in deep learning process and the modeling process for the downscaling concepts. First of all, every time you convert an image collection into an Xarray, if your dataset has a multi-temporal structure, you need to sort it based on a time to avoid any problem or irregular or any disorder in your datasets. So let's multiply to 1 to make sure that a new dataset created separating from the previous one. It's a kind of trick, nothing changing the dataset by doing this multiplication. Just I'm gonna try to separate this dataset from the previous one by a very simple equation. Experimentally, I learned that this process helped me to increase the speed of processing in the next step. Okay, let's run the variable. This part may take a little bit longer compared to the rest of the part because that's the step, the main step, the data converted into the Xarray format. But as soon as the new data set created, then we have no problem about the speed of the processing. If you find any problem in your code or programming, you can easily compare your code with mine. My code is available below this video on my YouTube channel, and then you can fix your issue easily. So now the data set is ready, and I can use actually to prepare this data for the modeling process. Before going into the modeling process, I need to convert the dataset format into data frame. So let's make a data frame of this dataset. I need to convert 10 kilometer datasets into a table format because the table format is really suitable for the analysis, but at the end we can convert it into array structure for the visualization and the rest of the things. So the dataset with 10 kilometer format, now as I have, let's convert it into a data frame, and remember to drop the no data values. Oh, sorry, that was my mistake. Let's run the data frame with 10 kilometer. You can see that's the same data set. But with the table format for the region of interest. But I think the study area is very low, is very small area. Let me to make it a little bit bigger because it is important to have enough pixels for the analysis as well. So let's run. You don't need to do any change in your code, just rerun each cell separately, everything repeating for the new study area. That's the benefit behind the programming. You can write a single program that applies on everywhere and no problem. You don't need to change anything. Just the study area updates and the rest of things remain the same. So I'm waiting. You can see that the sorting process taking a bit time, but as soon as it's done, the rest of the process doing quickly. So yes, Now the data set again prepared. Now we have a higher number of data here. That's much better than before, because if we don't have enough pixels for the analysis, we will face with some sort of challenges. Okay, now I need to separate the predictors and original variables. Make a new code here, and X for 10 kilometer data sets to from data frame with 10 kilometer data set, open two brackets and call the NDVI, EVI. These are predictors with higher spatial details. So the temperature daily, the day temperature, night temperature, evapotranspiration, and land cover, and digital elevation model or DEM. So this is the X with 10 kilometer resolution that you can see the precipitation excluded here. So we have the X values, but as you can see, they have different range of values. For the sake of the modeling in the deep learning process, I need to standardize the range of the values in all variables. The standard process helping us to have a same range or a same minimum or maximum in all data sets. Then it is easier for model to compare the values from one variable to another one. So that's why we need a new library from scale-learn, a new function from scale-learn library. So from scale-learn library, let's call the pre-processing and import standard scalar, just like this. So call a scalar function for X data with 10 kilometer resolution. So standard scalar, it sets to a standard scalar just like this. Now I need X for 10 kilometer data set that is standardized. Standard sets to a scalar function for X with 10 kilometer resolution, applies on by fit transform on X values from 10 kilometer resolution. So let's print like this. So as you can see, now I have the same variables but with array format, and their range of values, all of them standardized based on standard scalar process. Let's put the table a little bit upper like this. You have a preview from the first data set. Now I'm selecting the predictors for from X and converting into a standard format. Okay, let's do the same process for the Y or original variable. The original variable is precipitation. So the Y or original variable with 10 kilometer. From data frame with 10 kilometer, let's select the precipitation. Call a new scalar function for Y with 10 kilometer. Standard scalar again called. So Y with 10 kilometer in a standard format sets to get the function that is scalar Y 10 kilometer, apply Y transform on Y with 10 kilometer resolution. Remember to select the values. That's only the difference between a standard process between X and Y. So dot values dot reshape, we need to reshape it into a new structure. So what does it mean? Here we have y with 10 kilometer. So as you can see here, that's the first format. When you get the values, you will have a horizontal array of the values, just like this. And if you get the shape, here you can see the dimension. It has only one dimension, but it should have two dimensions. That's why we apply the reshape function. -1 and 1 convert it into a two-dimensional format, a vertical structure and two dimension. If you apply the shape, now you can see it's now converted into the two-dimensional structure. So that's why we apply this values and reshape on the precipitation and original variable. Okay, it's done. And y and x, both of them are available. Let's print y for 10 kilometer, the standard version, so you can see both of the values are available. In the next step, I need to separate the training and test values. Go to sklearn again. From sklearn.model selection, call train test split function. Now x train, x test, y train, and y test splitting by this function. Train test split x 10 kilometer standard version, y 10 kilometer standard version as well. The test size sets to 0.2, 20% of values considered for the validation process. The random state by default should be 42. That ensures the randomness strategy for the sampling process. So now we have train and test dataset for the modeling. The data prepared for the modeling process. Now we need to call a deep learning model. For example, the neural network is the most famous one. So from TensorFlow, hopefully it's available in the Colab environment. The TensorFlow.keras.models import sequential model, and from TensorFlow.keras. What was that? I think it's layers import dense. So now we have access to the sequential model, and we can call it like this. The model sets to a sequential structure. A sequential structure model is a kind of model that we can define the different layers by the dense. So the model can have a new layers like dense, add a new dense with, for example, 64 neurons, and input and activation should be activation. The activation function, typically ReLU function considered, a ReLU algorithm considered, and input dimension, the number of the predictors. How we can set the number of the predictors? So the number of the predictors already defined in the x with 10 kilometer. If you select the x values and get the shape, here you can see the second parameter, the second item showing the number of predictors, 7. So if I choose 1, inside the bracket the 7 selected. That's why we can add the input dimension as this format. So now let's run to make sure there is no issue here. Let's repeat the process again. So I have here 64 neurons to find the general pattern between the original and predictor's variable based on ReLU function. And the dense layer helped me to make a connection between the first pattern and the next pattern and information that's supposed to find in the next layers. So the dense, again, this time 32 neurons defined here with the same activation sets to ReLU. The ReLU algorithm ensures or guarantees the pattern will be transferred or transitioned into a next layer and help us to combine the information calculating by each neuron separately in different layers. So typically we think that higher number of the neurons and higher number of the layers will help us to find more information from a complex relationship. So again, a next layer, this time with, for example, 16 neurons activation. So the general information or pattern or the relationship will be found by the first layer, and in the next layer with lower number of the neurons, more complicated interactions or relationships or more detailed relationship between predictors and original variable considered. That's why we have a multi-level processing, and we are using different neurons separately. Model that add, finally we will have the final result with only one neuron, just like this. So now we need to compile the model. In the compile process, we should define the optimizer sets to the Adam, and the optimizer help us to associate the model performance based on statistical parameters like mean square error and mean absolute error. So the compile help us to know that when the model trained the relationship perfectly with the lowest error. Let's run the model. Model is prepared, but we need to fit the model between the X train and Y train. Model now applies on X train and Y train value. So, and there are the other parameters like, for example, the batch size. The batch size could be, for example, 8. The epochs. The epochs is the number of the time that model repeating the process, repeating the calculation. Higher epochs, higher number of recalculation, and vice versa. For example, I consider, for example, 50 times because I think that the repeating the process with higher number of values help the model to understand the relationship or find or figure it out the relationship between predictors and original variables with a better accuracy. And validation split could be, for example, 20%. Now I'm considering 20% of data to validate the model performance as well. And the verbose 1, it's a progress bar to show how model works. So the epoch number 1 is calculating. So as you can see, the mean absolute error and mean squared error, both of them calculating for each epoch separately, and the model finding the relationship between x and y in each epoch separately, and this process supposed to repeat it by 50 times until the mean square error and mean absolute error reach to a lower reach to a most stable level with the lowest differences between previous run and the next run. For example, in the first run, you can see a big difference between the loss function and also mean absolute error from the first to the second. But the differences is going down as the model repeating the process. It means that the model is learning the relationship, and this learning process help the model to predict the final result with the lowest error that is possible. And at the same time, the validation values, you can see all of them listed here, selected to calculate the model prediction performance. So that's how the model works. This process repeating for 50 times until the model harmonized and learned the relationship between the train and the test value. I'll pause the video for the few minutes until the whole of the epoch calculated completely. Then we resume the process and see and follow the next step. So as you can see, the process is done after 6 minutes and model trained, and you can see at the end the model reaches to the lowest change between MAE, mean absolute error, and mean square error for consecutive process. So now we can even evaluate the model performance as well. How to do this? Let's make a new variable like the model evaluation. Sets to call the model and evaluate its performance based on X test and Y test value. And you can see the mean absolute error and mean squared error that should be close to the 0. Their value ranges between 0 and 1. The values or smaller values here showing a better result. For example, the mean absolute error, meaning that the predicted values is about 0.4 units away from the original variable. That is acceptable here. So the model working well, and now the model is ready to predict the precipitation data with a higher accuracy. If you go back to the code, you can find the dataset with 10 km. Now it's a time to call this dataset with 1 km. Okay. Back to the next cell, make a new variable, this time with 1 km. From XR, the open dataset, the same collection, engine, CRS EPSG 4326. This parameter already explained well. That's why I'm doing quickly just to show the result. The scale is different. Previously, we utilized 0.1, but this time we need 1 kilometer. 0.1 means 10 kilometer. 0.01 here is the 1 kilometer. So now the same dataset calling with 1 kilometer pixel resolution. Let's repeat this process. Sort this dataset according to temporal dimension and multiply or times to 1. Now we are waiting to a new dataset separated from the previous one that guarantees the speed of processing in the next step. This time, some of the process may take a little bit longer because when you call the dataset with 1 kilometer resolution, definitely you have a larger number of the pixels to the analysis. So the process is done. Let's convert it into a data frame with 1 kilometer resolution. So get the DS win 1 kilometer, convert to data frame, just like this. Remember to drop the no data values. Something's wrong. Data frame. There is a typo here. The problem fixed, and now you can see the data frame for 1 kilometer dataset. As you can see here, we have a larger number of the values here or the number of the pixels compared to the 10 kilometer resolution, because here we have more spatial detail and higher spatial frequency or spatial detail. So again, we need to separate the X and Y for 10 kilometer data sets. So for 1 kilometer data set this time, sorry. So here we have X with 1 kilometer. From data frame with 1 kilometer, select the predictors. The predictors are NDVI, EVI, day temperature, night temperature, evapotranspiration, and land cover, and digital elevation model. This is 1 kilometer data set. X 1 kilometer. Now you can see the precipitation excluded here. Again, we need to standardize the X data with 1 kilometer resolution. So scalar X for 1 kilometer. Call the standard scalar again. So X 1 kilometer with a standard format. Call the function scalar 1 kilometer dot fit transform X with 1 kilometer. So call the standard data. Now you can see converted without any challenge. Do the same process for Y with 1 kilometer. From data frame with 1 kilometer, select the precipitation. So define a function, a standard scalar Y 1 kilometer. Call the standard scalar like this, Y with 1 kilometer and a standard format. So scalar Y with 1 kilometer, that is a function that fit transform on 1 kilometer data set while reshaped to 2 dimension. y 1 kilometer standard, just like this. Okay, the y and x, both of them prepared for the prediction, and the model is ready. So make a new code here and go to the main go to the data frame with 1 kilometer. Now we want to have a new precipitation with 1 kilometer as a new column in this data frame. Sets to call the trained model and predict the values, the precipitation values, according to standardized X values from 1 kilometer data frame. So remember that now the dataset is standardized and we need to actually return the range of value back to the main range that expected for the precipitation. That's why we need to use a scalar y function and apply inverse transform. Let's call the inverse transformation. Let me to check the code example to make sure everything's fine. So yes, inverse transform, that's right. Scalar, yes, there is a problem about the scalar y 1 kilometer. Now let's call the inverse transform and run the model. Let's run. So now as you can see, the model is calculating, or model is predicting the precipitation value with 1 kilometer resolution based on the neural network algorithm. The process may take 3 minutes or 2 minutes. Here you can see a counter, and then you will have access to precipitation data with 1 kilometer resolution. Okay, the process is done after 3 minutes. Now we can check the result. Data frame for 1 kilometer data. So a new variable added, precipitation with 1 kilometer. This is the range of value that is close to the precipitation values. Yes, you can see. So now I need to do a visualization. Definitely there is some changes between 1 kilometer and the original value or 10 kilometer data sets. That's definitely happen in the downscaling process, and we not expect to have the same range of values because 1 kilometer data is something predicted by the model, and definitely it's a little bit far from the original values. So let's convert the data frame structure into Xarray again because we want to do visualization here. So now dfx, or the result, sets to get the data frame with 1 kilometer. I need to select only 2 parameters, the original precipitation and precipitation with 1 kilometer. Dot to Xarray format, convert to Xarray format and sort it by time, latitude and longitude. Let's run. Okay, result is now ready. So 2 variables, original precipitation and predicted values. Select. Okay, I want to do I want to make a subset from the result. Result subset sets to, for example, one of the year 2020 is a year I want to compare the monthly precipitation. Get the result dot select for 2020. Call the subset variable. We have 12 precipitation data. Select the original precipitation first and make a plot. X-axis longitude dimension, y-axis latitude dimension. Call temporal axis sets to time, and robust sets to true. Let's run. And remember to add call wrap sets to 6 to have at least 6 map per row. Let's run again. Okay, now this is original precipitation data sets, and the values ranges, the value range is about the millimeter per hour. Now I need to have result for precipitation with 1 kilometer resolution. Make a plot, X longitude, Y latitude, and call sets to time, robust sets to true, and call wrap sets to 6. Let's run again. So here we have the precipitation pattern with higher spatial detail that you can see. For example, in 2020, November 2020, you can see the higher precipitation in these areas. You can see that with higher spatial details. Or in some of the months like May, June, and July, there is lower precipitation that you can find it here. So as you can see here. And yes, and also in the initial months, in the January, February, or April, we have the higher precipitation amount that is easily detectable in our data set as well. So now you can see how precipitation analysis, how the precipitation downscaling works in the Earth engine, and I hope you liked this tutorial as much as I did. If you had any question or problem about this tutorial, you can share your comments on my YouTube channel, and please share this tutorial with all of the remote sensing fans in all around the world. Thank you for your attention.